So today we are going to talk about set theory. All right. So, so what are we going to talk about? We are going to introduce the concept of sets. We're going to talk about sets and subsets. We'll see set operations. We'll see how to count the sets properly. Uh, we'll see what is Venn diagram, inclusion exclusion principle, and then we'll see application of this to finite probability, some conditional probability, and perhaps some expected values. Okay. So these are the few topics we are going to deal with. All right. Now, another thing I want you to keep in mind while doing this is look at the laws of logic. Try to build the dictionary of laws of logic and the dictionary of sets. They are very, very similar. Okay. So you should, we will discuss that again as we move further. Okay. So let's have a formal discussion of set. So set is a theoretical structure which is used to group objects together. Or you can say set is a well-defined collection of objects. All right. Yeah. So how can set be given? Like say, for example, I can give you a set. Let's say set A is given by say 1, 2, 3. This is an example of a set, right? It is a set with 3 elements, 1, 2, 3. Okay. Then we can have another, say another description of set. We can say a set of all prime numbers less than 10. Yeah. This is another way to describe the set. Okay. We don't want to go into specifics of the names. The first method is listing all the elements out. All right. Second method is basically describing the elements, right? You're describing what are the elements, right? So the set of all prime numbers less than 10, you know that it's 2, 3, 5, 7, right? But this is another way of listing a set. One more way is a constructor way. Basically, we say, okay, set is 2K where K belongs to Z. So it's collection of all 2Ks where K belongs to Z. Yeah. So you always represent set by curly bracket like this. So you have a curly bracket. Yeah. Uh, this is read as such that. Yeah. So it's 2K with what? What is 2K? K is an integer. Such that. So you read this as it's all 2K such that K is an what? K is an integer. Does that make sense? Yeah. Now, the objects or the elements, so objects of these sets basically are called elements or members of set. Okay. So for example, this set A, what are the members of the set A? Set A has 1 as a member, 2 as a member, and 3 as a member. Yep. So set collects, so these 1, 2, 3 are called members of the set. Is that okay? Now we can say that if I go back to set A, let's take this example, 1, 2, 3, inside the curly bracket, we can say that 1 belongs to A. So this symbol is read as belong. Okay. Why? We need symbolism, right? Symbolism makes our life easy, right? I mean, because I mean, what is addition? Addition is a symbolism, right? 5 plus 7. Yeah. Idea is that you take 5 and you take 7 and then you combine, put them together and count it at once, right? But the plus as a symbolism makes it easy. So similarly, there's symbolism. 1 belongs to A. Yeah. Now let's take 5. 5 does not belongs to A. So I'm going to write does not belongs to A. So you put a belong sign and then you put a cross out. Yeah. So we say 5 does not belongs to it. All right. So, all right. So, so that's the meaning of whether an element is a member of some set or not. Right. Now, there is one special set which is an empty set. So consider the following set. The set has no element inside. So this is an empty set. So it is represented by having two curly braces but nothing inside, right? Or you can represent A to be 5, like that, okay? So this is a notation used to represent an empty set, all right? So these are a few ideas behind basically set. Now, few important sets which we use all the time in mathematics or computer science or other places as well. The first one is set of integers. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all those positive ones. Then you have negative of those, -1, -2, -3, so on, and then 0. So set of integers basically are represented by Z. Yeah. I think it comes from the word, German word Zahlen, and Zahlen means numbers. Okay. So this is set Z, which is set of integers. Again, it's given by, say, 1, 2, 3, so on, so forth. Then 0, -1, -2. All right. Then we have set N, which is set of natural numbers, but you can say a set of non-negative integers, right? So in this case, we will have 0, 1, 2. Yeah. So this is set of what? Set of non-negative integers. All right. Now we have a notation Z plus. This is a collection of all positive integers. So note that this notation is slightly different when they come to mathematics. Okay, this is a notation very what do you say, common to computer science. In mathematics, it's actually natural number starts with 1, 2, 3, 4, 5, 6, 7, 8, and nobody talks about Z plus. All right, so it's natural numbers, and sometimes in mathematics 0 is included in the natural numbers, sometimes it's not. It's just a matter of convention, right? Okay. Then we have set of, so I can write Z plus as a subset of, I can say Z plus is collection of all those X such that X belongs to Z and X is greater than 0. Yeah, this is another way to write Z plus coming from Z. Yeah. Now you can have set of rational numbers, which is Q, which is given by all those X divided by Y, where such that X and Y are integers, and the only thing we do not want is to divide by what? 0. So this is a set builder form for rational numbers, right? So rational numbers are one integer divided by another integer. The only thing you're not allowed is to divide by 0. So this is Q. Now similarly, we can have Q star. Q star simply means basically all those element X such that X belongs to Q and you don't want X to be 0. Yeah. So our interest only lies until Q, maybe Q star. When you're given Q star, it will be defined to you clearly. So you don't really need to worry about these notations as such. Okay. And then we have R to be set of real numbers. R star is set of non-zero real numbers. C is set of complex numbers, and C star is set of non-zero complex numbers. Okay. But as I said, I mean, like we are not going to, for our purposes, mostly we will restrict ourselves to talking about Z plus, or maybe we'll go to Q, but nothing more than that. All right. Yeah. Because we want to do some discrete math, and discrete math does not work well with R. All right. Few more definitions. All right. So again, like any sciences, when you start with something new, you have to give definitions. You have to make the boundaries of your statements clear, right? You want to make things precise, so you must define things. So now, so given a set A, so if I give you set A, this represents the cardinality of the set. So given a set A, cardinality or the size of set A is the number of elements inside the set. Yeah. So for example, if I give you A equals to 1, 2, 3, then cardinality of A is what? 3. Because there are how many elements inside? 3 elements inside. Does that make sense? Yeah. Similarly, if I give you A to be an empty set, then cardinality of A is 0. Yeah. It has no elements inside. So the size of such a set is 0. Does this make sense to you? Okay. So this is about cardinality. Now, similarly, let's look at Z or Z plus. What is the size of Z? Size of Z is infinity, right? It's an infinite set. Now, it's an interesting phenomena. You can see, if you're interested, that there are different sizes of infinity as well. Infinity comes in different size. We can talk about it later if you want when we talk about power set. The idea is that infinity, so size of Z is also infinity. Size of real numbers is also infinity. But the size of real numbers is bigger than the size of Z. Okay, just a tidbit, not related to us. Yeah. So Z is countably infinite, and R is uncountable. Okay, whatever it means. But I just want to give you a gist that that there are sizes of infinity which are not same. Yeah. So Z is so R size of R is strictly bigger than Z, and then it can keep on going up and up and up. Okay. So anyway, now, so this is the idea behind the sizes of the set. All right. Now, we want to talk about subsets. All right. So again, for set also, we are interested in the universe. Although we don't talk about it explicitly all the time, but we have an idea of universe in mind when we are talking about sets. Say, suppose I want to talk about set of odd numbers, and I want to talk about set of even numbers, and I want to talk about set of numbers which are multiple of 5. I want to talk about set of which are multiple of 6, 7, 8, 9, 10. When I want to talk about collection of all these sets, I should have some universe in my mind where they all live in. Is that okay? Yeah. So that is the idea behind the universe. But we will see more examples later on. So suppose we have two sets from the same universe, U. All right. The universe is possibly all collection of elements you are interested in. Then we say that A is a subset of B, right? We say A is a subset of B, and the notation is A is a subset of B. If what happens? If X belongs to A implies X belongs to B. Let me give you an example from the perspective of, suppose I have set A is 1, 2, 3, and my set B is 1, 2, 3, 4. Then you can clearly see that A is a subset of B. You agree? Yeah. So here we have, if X belongs to A, then X belongs to B. This is the definition. Yeah. And now you can think about this as a logical statement too, right? This is an implication, no? X belongs to A is a proposition. It can be true, it can be false, depending on X, right? So if X belongs to A, implies X belongs to B. This is what? This is a logical. So you see the connection with the logic, right? So this implication is equivalent to A being a subset of B. Right? Now, sometimes you want to talk about strict subset. Strict subset means A is strictly inside B. Yeah. For example, this is true. A is a subset of A. Right? You agree? I mean, if X belongs to this A, then of course X belongs to A. Right? So that is true. Right? So sometimes we want to talk about the proper subset. So in that case, what is the meaning of proper subset? So A is a proper subset of B. So for proper subset, people write like this. So proper subset. Some book also use this. So they will say A is a subset of B, and then they will cross this out, just to indicate that it's a proper subset. All right. So A is a proper subset of B if what happens if, now let's write this logically. If X belongs to A, implies X belongs to B. So that should be true for sure. But what should happen? That that B should have some element which is not in A, right? So we can say this, and there exists, say, X or Y belonging to B, such that Y does not belongs to. Then this gives me a proper subset. So gives me a definition of proper subset. Is that okay? So this is the definition of proper subset. All right. Again, a lot of definitions. Again, why? Because we are building a vocabulary now. Yeah. And as you have seen in the problem, if in your divisibility problems, right? We in mathematics we have to make definitions clear so that all the results we are going to prove follow from those definitions. All right. So now, next one. So now, when do we say two sets are equal? Two sets are equal if they have same number of elements, not just same number. My bad. Same elements. Yeah. Not just same number of elements. I mean, you could have set A, have one set having A, B, C, and the other one set could have 1, 2, 3. They may have same number. They have same number of elements, but they are not equal. Yes. No. So in set, the order of element does not matter. Yeah, that's another fact, because it's just a collection of objects. Okay. Yeah. So A is equal to B. Yeah, we say A equals to B if what? If X belongs, so we have A equals to B. When do we say that? If X belongs to A, so X belongs to A is same as saying what? X belongs to B. It's a bidirectional. Yeah. You can also say that X belongs to A implies X belongs to B, and what? Yeah, and X belongs to B implies X equals belongs to what? A. Another way of looking this would be what? It would be A is a subset of B and B is a subset of A. Yeah. Again, this is not a proposition, so I'm basically hesitant to write it like this, but A is a subset of B and B is a subset of A. So a lot of technique for proving that two sets are equal rely on saying A is a subset of B, and then you show B is subset of A. And when you are able to show this both together, then you have proven that A is equal to B. All right, so this is a common technique for showing that two sets are equal. Now, so next thing is basically talking about the idea of the Venn diagram. All right, so what is the idea behind the Venn diagram? So Venn diagram is useful to show the relationship between sets. Yeah. That okay? So basically that is depicted by Venn diagram. All right. So for example, so I have set A, which is say 1, 2, 3, 4. I have set B, which is say 1, 7, 8. Then I want to show you this in Venn diagram. I will have universe U like that. I have set A, I have set B, and then I can say 1, sorry. So 1 is common. Then I have what? 2, 3, 4, and I have 7, 8. So this is a Venn diagram way of basically, yeah, of showing that these two sets are basically part of it. Yep. Does that make sense? So now we want to basically talk about the set operations. Okay. So before I go further, I want to make sure I'm covering everything. That's why I'm having a look at this. Right. Okay. Now, Two sets can be shown that they are equal in how many ways? So these are the ways we can show. One is a tabular method, where you have a membership table. We'll look at some examples, all right? One is the algebraic method using law of set theory. So like you have laws of logic, all those laws of logic have equivalent set theory setup, okay? For example, you have, just let me, and we're going to make it more precise, but I just want to make sure that we get hyped about this. A or B is same as, for us, logically, this is equivalent to what? Negative P and negative Q, right? So there is an equivalent statement. So this is De Morgan's law. There is another statement of De Morgan's law where you take the complement. We have A complement, B complement, exactly like this, but with the intersection. All right. But before I talk about this, I need to define for you what does complement means, what does union means, what does intersection means, right? But what I mean to say is that the first law and the second law, they both are called De Morgan's law because they are exactly the same laws. Yeah. So let's embark on this journey of what using what these methods to do some set operations. All right. So let's talk about unions and intersections first. So let's say I have set A equals to 1, 2, 3, 4. I have set B be 1, 5, 6, 7, and let my universe U be 1, 2, 3, 4, all the way to what? 10. Okay. So first thing is to talk. So first thing I will talk about is the complement. All right. So A complement. So A complement. So this is read as A complement. You can also say complement of A. Yeah. So if I look at from Venn diagram perspective, I have A here. Yeah. This is my universe U. Then everything outside is what? A complement. So this is my A complement. All right. So if I'm given the universe U, then in this case, for example, my A complement is going to be 1, 2, 3, 4 is in A. So what is in U, which is not in A? So I can write this also as U minus A. Again, this is not a number minus, this is a set minus, all right? Now, what is the meaning of set minus? So set minus is from U, you will remove all the elements which are in A. Is that okay? So U, from U, remove all elements which are in set A. So A complement is going to be U minus A, which is going to be, if I want to write this down, it's going to be 5, 6, 7, 8, 9, 10. Right? You agree? So that is A complement. By the way, what is U complement? Anyone? Empty, right? And what is empty complement? U, right? Now, so here's a few more things. So let me call, before I go further and talk about, maybe let's talk about union. So A union B, what is A union B? It's all X such that what? X belongs to A or X belongs to B. Perfect. Yeah, or X belongs to. All right. Now, what is this X? Where is this X coming from? The X must come from what? The universe, right? So I must add something here about saying that, oh, I'm not taking any X. Where am I taking my X from? The universe. So all X belonging to universe U, such that X belongs to A or X belongs to A. All right. You will say, okay, oh, why did you write it here? Can we write it here? Yes, you could have written this here as well. X belongs to U and X belongs to A or X belongs to B. Yeah, makes sense, right? People generally don't write this because it's kind of clear. People generally avoid that writing because people know that it's clear. We are discussing, when we are talking about set theory, we have a universe in mind and it's fixed for that problem. Yeah, makes sense, right? Now, what is the intersection? In this case, the union is going to be, let's just work it out. So A union B in our case is going to be 1, 2, 3, 4. So I can write it 1, 2, 3, 4, and then 5, 6. Yeah. In sets, we do not repeat the elements. Yeah. What if an element is repeated? It's no harm, but we do not repeat the element. All right. Because if you repeat the element, then while counting, you may be in trouble, right? If you have set, say, suppose let's take set with 1, 1 in it. The size of this set is still 1. Yeah. Just because you choose to rewrite 1 many times. Yeah. So that's why people try to have a minimal representation. Does it make sense to you? Yeah. Minimal representation means every element written exactly once. Yeah. Now, if I want to basically draw the union, how will it look like? So I have set A, I have set B. So this is my set A, this is my set B, and I'm in the universe. This is my universe U. Then set A union B is, this is my A union. Yep, right? This thing is my A union. All right. So similar to union, there's a concept of what? Intersection. So what is an intersection? Intersection is what is common in both of them. So if this is my set A, this is my A intersection B, right? So I have A, I have B in universe U. This part is my A intersection B. So what is common in both of them? All right. So how will I write it? For our example, it will be, we have what in common? A, we have only one in common, right? So A intersection B is simply 1. Yeah, makes sense? Now, what could be the definition of A intersection B? The definition is of A intersection B is all those X belonging to universe U, such that what? A and X belongs to what? This is the concept of intersection. So far good? Yeah. Now we want to talk about generalized union and generalized intersection. What do I mean by that? We could think about million sets and have intersection of million sets, right? Or we could have union of million sets, right? We could have infinite number of sets and we could have union of infinite number of sets. We can also have union of infinite number of sets as well. Not only that, we can have union of uncountably infinite number of sets and intersection of uncountably infinite number of sets. Okay. So therefore, we have to come up with the concept of index now. Okay. So index is basically you have sets and you want to label them. You don't want to call A, B, C, D, E, F, G because you will, after 26 alphabet, you're done, right? But suppose I want to talk about billion sets. So a proper way to label them would be what? A1, A2, A3, A4, A5, A6, blah, 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 all the way to A billion. Yeah. Sometimes you want to basically label the sets in a different way. Yeah. So that's what is the job of indexing set. Yeah. So for example, I can have say A1, A2, A3. So my indexing set is what? I is my indexing set, which is 1, 2, 3. Yeah. It is giving index to the set. Index means basically it's giving some It's helping us basically define all these different sets. Okay, so that is an indexing set. All right, you could also have the following: I to be, again, this is slightly funny, but monkey and say fox. So this could be our indexing set. Then our sets will be what? A monkey, A fox. These are used to label those two sets, right? Does that make sense? So indexing set can be anything. It could be A, B, C, D as well. It could be alpha, beta, gamma as well. Yeah, yeah. So you will see again, if you choose to do some mathematics later on, you will see a lot of it shows up. The indexing shows up a lot. Yeah. All right. So now, what would be a reasonable generalization of union when we are doing indexing, right? So if I have a set, I want to talk about union of I belonging to I of AI. If you think about this, you may say, oh, what is this I belong to I? If it makes you slightly uncomfortable, it is just saying that I'm taking union of all these sets. They are labeled by what? Index. Yeah? So you can think about it just to be comfortable. When you start, you can think about I to be 1 to 10, for example. Yeah. So then when you talk about union, you're talking about union of 10 sets, A1, union A2, union A3, union A4, union A5, until A10. All right. So what is the union of this would mean? It's collection of all those X belonging to you such that X belongs to AI for some I, right? Or for some I belonging to. Yeah. All it is saying is that union is collection of all those elements in the universe such that what? X belongs to some AI. It could belong to 1, 2, 3. It could belong to just one, or it could belong to all of them. It doesn't matter. Yeah. Union means it must be there in at least one of them. Then it basically classifies to become a part of a union. All right. Similarly, we can have the concept of intersection. So as you can notice in this lecture note, we stopped basically talking about X belonging to you. Right? Because the idea is clear. When we are talking about it, we are always interested in what? In the universe. We don't want to exceed the universe, right? So after some time, people drop the using X belongs to you, right? So we can drop it too if you want. So what is intersection of I belonging to I of AI? So intersection means what? All X such that X belongs to AI for all I in I. Right? This means that it's common to all of them. That is the difference, right? So this is a concept of union versus intersection. Does this make sense to you? Yeah. So, yep. All right. So let's move back a little bit. A lot, actually. Now, so we want to have some laws of sets now. All right. So these are few laws. So few theorems based on whatever we learned so far. So it says what? If A is a subset of B and B is a subset of C, then A is a subset of C. Does that make sense? If A is sitting inside B and B is sitting inside C, then what? Then A is a subset of C. Right? No, they are just one is sitting inside the other. So we can have the following, right? So we can have A is sitting inside. Let's just say A is sitting inside set B, right? And B is sitting inside set B is sitting inside set C. Yeah. Then can we say that A is inside set B, set C, right? So this is a Venn diagram proof of this statement that if A is a subset of B and B is a subset of C, then A is a subset of C. All right. Now, since we do not have here we have a equal to sign. So it could be that A is equal to B and B is equal to C, or A is equal to C, right? So when you have this sign, it means that two sets, one is subset of the other. It may be a proper subset, may not be a proper subset. Yeah, it's like saying like this, right? 2 is less than equal to 3 and 3 is less than equal to 4. This implies what? 2 is less than equal to 4, right? Isn't it? Yeah. So it's a or condition, right? 2 is less than or equal. So proper subset is what? A is contained or is equal to B. So now, if I want to write this as a logic statement, let's see, how do we go about it? So we have, let's translate this into logical statement. So if X belongs to B, if A is a subset of B, what is the logical statement of that? If X belongs to A, implies what? X belongs to B. Do you agree? Yeah. Or you can say, or if you want, you can also say, for all X belongs to A implies what? X belongs to B, right? Similarly, we can have the second line is going to be what? So this is let me just write it in a different color. This is the equivalent of statement A, right? Similarly, B is a subset of C. What is an equivalent logic statement of that? For all X belongs to E. Maybe I should use the same color then. For all X belongs to B implies X belongs to C. Now, what is the outcome of these two statements? And with what law can I? So think about this as a statement Px. This is Qx, right? So we can think about this statement as Px. So now, so we have this statement can be Px, this can be Qx, this is Qx, and then this is what the Rx. Then how can we connect Px with Rx? Do we remember any law? Law of syllogism, right? Law of syllogism said what? If P implies Q and Q implies R, therefore P implies R, right? So from there we can get, therefore for all X we get Px implies what? Yeah, isn't it? Or in this statement, it would be for all X, we have X belongs to A implies X belongs to C. Yeah. Or in other words, if you want to convert it into set theoretical setups, it's going to be A is a subset of. All right. Okay. Similarly, if A is a strict subset of B and B is a subset of C, then A is a strict subset of C. Yeah. So what does it mean? It means the following. Let's try to look at this. We have, so what? How do we convert this statement into logic statement? So we have X is a strict subset of A, right? This means what? X, if for all X belongs to A, implies X belongs to B, right? And on top of this is not it, right? Strict subset means what? There exists X such that what? Such that there exists X such that X belongs to A, sorry, X belongs to B implies, yeah, exactly, X does not belongs to, or we can say and right here. X belongs to B and X does not belongs to A. Does make sense to you? Yeah. So this is another law. And the next one, so next one is if B is a strict subset of C, what do we get in that case? For all X belongs to B implies what? X belongs to C, right? Yeah. So what do we get out of this statement? So first of all, we get what? From the first line, we will get what? We will get for all x belonging to A, for all x, sorry, x belongs to A implies x belongs to what? C, using 1 and plus 2. Do you agree with that? Yeah. So this is previous to the same as the first one, right? So this is because of law of what? Law of syllogism. This together with, I'm going to write and, because that's what, when you write two things together, right? This means what? And first statement and second statement and third statement, right? This is what is the meaning of when you write them in line like that. It's first statement and second statement and third statement. So I'm just going to repeat this statement here. That means what? There exists x, but x belongs to B. So we can replace this as what? X belongs to B, same as saying what? C, right? X belongs to B implies x belongs to what? C. Do you agree? Yeah. Makes sense, right? So what can we say basically? We can say if there exists x which belongs to B, not an A, this is the same as saying there exists x belonging to C, but not in A. So if you combine, let's say 4 and 5, you will get exactly the result that what? This is a definition of A is a strict subset of C. Or you remove that line. This is what you get. As a Venn diagram, it will simply look like the following. You have A is a strict subset of, A is what? Strict subset of B, right? So you have A, and then you have B. There's this extra element left out here. And then B is subset of C, like that. Yeah. So then you can say that A is a strict subset of C because this element is in C, but not in A. Yeah. Is that okay? Yeah. Yes. So strict means it's like father and son, right? So strict has an order to it, right? So A is a strict subset of B. So let me just write it down again. So A is a strict subset of B. It means what? It means, first of all elements are there of set A are in set B. But there's an extra condition on top. That means there is at least one element in set B, which is not in set A. Okay? That's right. So it is same as X belongs to A implies X belongs to B. And there exists element in B which is not in A. So it's with an extra condition. Yeah. So you can think about this as an extra restriction. All right. And then there are other ones right here. Okay. Now let's look at this theorem here. So let's look at the following theorem. The theorem says that if you take any set, empty set is sitting inside. Okay. So the idea is that empty set is a subset of all sets. Yeah. In fact, if a set is non-empty, then empty set is a proper subset of that guy. Okay. So I want you to think about this, and we can talk about it after the break.